This is the third lecture on interpolation. Today we shall discuss Lagrange's interpolation formula, which is applicable for equal as well as unequal values of x. Note that there was a restriction in Newton's forward formula. Newton's forward formula can be applied only for equispaced x values, and here the Lagrange's interpolation can be applied to equispaced as well as non-equispaced values of x. The basic problem is same. We are provided with n plus 1 pair of data with I is equal to 0, 1 up to n. So we are provided with n pair of data, and we can approximate y of x as a interpolating polynomial of order n. In Newton's formula, we assume that the polynomial to be like this. Newton's forward formula. This was the assumed form in Newton's forward formula. Here we assume the polynomial to be like this. Note carefully, it is x minus x1, x minus x2, right up to x minus xn plus a1, x minus x0, x minus x2, x minus xn. For a0, there is no x0 term. For 1, there is no x1 term. ai, x minus x0, x minus x1, right up to x minus xi minus 1. Then the next term is xi plus 1, and then x minus xn. The last term of this series is x minus xn minus 1. This is the polynomial in Lagrange's method. Lagrange's interpolation formula. It is seen that at the first sight, this formula appears to be a bit cumbersome compared to it, but it will be found that this formula, so far as computer implication is involved, is very systematic one. We can write it in a compact form as summation over I is equal to 0 to n ai, then the product term goes to j is equal to 0 to n, with prime means j not equal to I. This prime stands for the fact that j is not equal to I, x minus xj. So this signifies that j not equal to I. This is the simple formula, and if we want to find out the coefficients, as usual at phi n at x is equal to 0 is y0. you see that all the terms except this one 0 is 0 because it involves x minus x0 term. So at x is equal to x0 they become 0 and we get a0 is equal to x0 minus x1, x0 minus x2 right up to x0 minus xn, or we have a0 is equal to y0 divided by this one x0 minus x1, x0 minus x2 right up to x0 minus xn. So there is no x0 to x0 term for the second of the binomials, each of the binomials. Similarly, if we put xn is equal to phi at x is equal to 1 is y1, this is the basic requirement of any interpolation formula, that at each of the supplied x values the interpolating polynomial exactly matches with the corresponding y values. There is no estimation. As you put x is equal to x1, all these terms vanishes except this, and the result is or a1 is equal to y1, x1 minus x0, x1 minus x2, x1 minus xn. Proceeding similarly, we get phi n at xi is equal to yi, and all the term except this vanishes and we get it as ai xi minus x0 right up to xi minus xi minus 1, xi minus xi plus 1 xn, which gives ai is equal to, or ai is equal to yi divided by xi minus x0, xi minus xi minus 1. The next term is xi plus 1, and then I'll write up to xi minus xn. We can write it as yi summation product of j is equal to 0 to n with j not equal to I xi minus xj, and that value of can be incorporated there, so that this formula becomes this very formula with ai being replaced in the numerator. We will have this factor, and in the denominator we have this factor. So this is x minus xj divided by xi minus xj. This is the Lagrange's interpolation formula is as simple as this. Now we can, let me explain the steps once more. The interpolating polynomial, which is an order polynomial of order n, is chosen in this fashion. In the ith term ai, the expansion coefficient ai is multiplied by a polynomial of degree n, and x minus x0, x minus x1, all terms are there except there is no x minus xi term in the ith contribution, and that is we have written it in a compact form ai where I runs from 1 to n, and for each I j runs from 0 to n excluding I, that is being denoted by the prime. And the requirement that at a particular given value of xi for the polynomial, the interpolating polynomial exactly reproduces the corresponding y value enables us to find out ai in this form, and if we write this value, this is the formula. This is the compact formula for Lagrange's interpolation formula. There is no need of the requirement that the x values should be equispaced. They may be equispaced or may not be. Now, with this we shall apply the formula to a specific case. First, let me write the formula. Phi n in Lagrange's formula is written as I is equal to 0 to n y I, then product j is equal to 0 to n excluding j is equal to I. In the numerator we have x minus xj, in the denominator we have xi minus xj. This is the formula. Now we shall apply the formula to a specific case. Now we apply the formula to the given set of data. There are 4 data given, so we can fit the given data into a polynomial of degree 3. So the polynomial is written where I ranges from 1 to 3. Writing explicitly, this becomes y0 times x minus x1, x minus x2, x minus x3, x0 minus x1, x0 minus x2, x0 minus x3, this is the first term, plus y1. Then we have x minus x0, x is equal to x1 is not there. Then x1 minus x0, x1 minus x2, x1 minus x3. This is 3 plus y2 x minus x0, x minus x1, x minus x3 divided by x2 minus x0, x2 minus x1, x2 minus x3 plus y3. X minus x0, x minus x1, x minus x2, x3 minus x0, x3 minus x1, x3 minus x2. This is the explicit form of the formula when written for a 4 data set. We want to find out the value at x is equal to 5. So what is the value of, this is our question. If we were using the value, this same thing in forward in Newton's formula, this data become the result would be inapplicable. Firstly, due to the fact that x values are not equispaced. Secondly, the value of x chosen lies at the middle of the range. So in that case, Newton's forward formula has less accuracy, but there is no such restriction for Lagrange's formula. If we write this value, then this becomes phi n at x is equal to 5. So y0 is 1 into 5 minus 0, 5 minus 7, sorry, 5 minus 1, 5 minus 3 for x1, 5 minus 3, 5 minus 7, 5 minus 10. Then we have 0 minus 3, 0 minus 7, 0 minus 10 plus y1. For y1 we use the value 31. Then this is 5 minus 0, x minus x0, x minus 7, x minus x2, x minus 10, then 3 minus 5, 3 minus 0, 3 minus 7, and 3 minus 10. These are three values. Then y2 is 351. 5 minus x0, 5 minus 3, 5 minus 10, then 7 minus 0, 7 minus 3, 7 minus 10, plus 1011 times 5 minus 0, 5 minus 3, 5 minus 7, then 10 minus 0, 10 minus 3, 10 minus 7. On explicit calculation, this comes out to be 131. If we perform this calculation, it comes out to be 131. We could also feed the data into a polynomial like this. Psi n is equal to psi n of x is equal to b0 plus b1x plus b2 x square plus b3 x cube. As there are 4 data, we cannot choose a still higher power of x, and we have used least square fit method to feed the data in a computer, and we found that data comes out to be 1 plus 1 into x plus 10 to the power minus 14x square plus 1 into x cube. That is to say, this b2 is 0 and the formula is 1 plus x cube. You see that this data exactly matches with this. If we were provided with still higher values, say fourth value of x in this range, which is at par this, then we could introduce b4, and the value of b4 would also come out to be very small, signifying that the b4 term is not significant over there. Even if the x square term were in the range, but the calculation shows the x square term is insignificant. If we could calculate the coefficients and then we collect the power of x square in this formula, in the Lagrange's formula, it will also lead to zero values for the given set of data. The point that I want to remind you that even if you assume a polynomial which is of higher degree than the actual one, you need not to bother. Those coefficient or those power of x which do not contribute to the polynomial will come out to be 0, but in numerical calculation, due to the truncation error, the value may not be exactly 0, but they would be insignificant in comparison with the others. As for example, here b0, b1 and b3 are 1, while b2 is much smaller than the rest, signifying that b2 is 0. The problem that lies within in this formula is that if you do not have sufficient number of data, as for example, if we were not provided with this data, the polynomial that we would have will be up to second degree, and if we use a polynomial of second degree, this data cannot be fitted very well because the actual data had a cubic term, but due to insufficient number of data we could not afford a cubic term in the interpolating polynomial, and the result has to be in error. As I have pointed out in the first class, that if we were provided with the data of coronavirus cases in India, say up to September or it's up to October or November, then we found that there was a consistently increasing trend by day. With those data, we could not get the lowering trend. The lowering trend has obtained only if you have sufficient number of data. So this much with the Lagrange's interpolation formula. In a next class, we shall discuss the algorithm for the Newton's forward interpolation formula and Lagrange's interpolation formula.